And 26.3, total internal reflection. So when light is passing from a medium of larger refractive index into one of smaller, the refracted ray will bend away from the normal. So an example of that is if instead of having light in the air section, if the light's in the water passing towards the air, then some of that light ray will naturally just reflect at the interface. But a lot of it will pass right through the interface being boundary between the water and the air. And as it passes into a smaller refractive index, it's going to bend away from the normal to a larger angle. This will always happen. Well, if we keep increasing this incident ray angle, theta 1, to larger and larger values, at some point, you get an incident angle that creates a refracted angle that's so large, it's actually at 90 degrees. This is known as the critical incident angle. So the incoming light, in order for it to refract properly following Snell's law still, it's going to refract at theta 2 is equal to 90 degrees. And at this point, none of the light is able to pass through the interface. It is only reflected. If you go to any angle above the critical angle, there's no more even refracted at that 90 degrees angle. This is known as total internal reflection, where all of the light stays within that medium of higher refractive index. Like all of the light stays within the water and isn't able to make it out to the air. You can plug in the condition to Snell's law in order to find the critical angle. If you have n1 sine of theta 1, which we're going to call theta c here, is equal to n2 times sine of 90 degrees at that critical angle. Sine of 90 is 1, and so that disappears. If you divide the n1 over to the right, then you have that sine of the critical angle is equal just to this ratio of n2 over n1, where n2 is the secondary medium that the light's trying to get to and cannot. And n1 is the initial medium that has the higher refractive index. See, it even shows it over here on the right. This is part of the equation. n1 must be greater than n2 for this equation to work out. And there's an example of this actually in this strange looking photo. This is an underwater photo of a salamander. So we can see the salamander underwater, cool. And then there's air above. And because some of the angles of the light coming off the salamander coming at this interface are larger than the critical angle, there's reflection. And so we're seeing a reflection of the salamander. The boundary between the water and the air is acting like a mirror and reflecting an image of the salamander there for us to see. Pretty cool. So let's look at an example of total internal reflection, which is abbreviated TIR. A beam of light is propagating through diamond and strikes the diamond air interface at an angle of incidence of 28 degrees. Will part of the beam enter the air, or will there be total internal reflection? B, repeat part A, assuming that the diamond is surrounded by water. So we notice the first step here is drawing a picture, and they show the light propagating through the diamond, so that's what we're focusing on. And then we want to know when it strikes the diamond air interface, if it will then enter the air. So that's important to note, that's the boundary. And they give us this angle of incidence. Okay, so we want to know, is the angle such that it will? And will that change if it's surrounded by water? Well, based upon our critical angle equation, we can solve for theta c with the inverse sine of just the ratio of those two refractive indices. So for air, it's just 1.00. That's the secondary one where the light is trying to get to the air. For a diamond, it's 2.42. It's pretty large. And so the critical angle is 24.4 degrees. Now our entering light is incident at an angle of 28 degrees, which is greater than this critical angle. Because our incident angle is greater than the critical angle, we have total internal reflection. And that's what's depicted here in the picture, where the entering light is at this red line, and it's greater than the critical angle, and so none of the light is able to pass into the air, and it instead reflects and stays within the diamond. If instead we're in water, that changes our N2 to 1.33, and thus our angle becomes much larger, 33.3 degrees. In this case, our incident angle of light of 28 degrees, which hasn't changed, is less than the critical angle. And so we're only going to have refraction here. There still will be a small amount of reflection as before, but we aren't going to have total internal reflection as we did in case A. This has important implications for diamonds and part of why diamonds are so valuable. So the diamond is famous for its sparkle because the light coming from it glitters as the diamond is moved about. Why does a diamond exhibit such brilliance? Why does it lose much of its brilliance when placed underwater? Well, if we think back to this example that we just saw, in air, the entering light gets totally internally reflected, and now this light ray is passing up. That's going to produce a bright sparkle if you happen to be looking at that angle, or maybe it reflects off there and comes up to your eye in a different way. So in air, because of this total internal reflection, a lot of the light from above is able to then be reflected back up to the eye from all sorts of different interesting angles. In water, however, because it increases the critical angle, a lot of the light just passes right through. And then the diamond looks more like glass. It looks like a fake, which is much less valuable and much less interesting. So that's one reason why diamonds are so valuable. Another application here of this total internal reflection is actually using prisms to use it within like binoculars, that they can totally redirect the light. If you have incident light coming in at an angle greater than the critical angle, then none of the light will pass through the glass on the other side. So this isn't a mirror here, it's just the actual difference in the material. And so it's going to totally reflect at that interface with the air, and it will make a right angle. So you can totally change the direction. If you have two such triangles, you can have light that's coming in one way, reflects and is shifted upward, and then goes out the other way. And that's shown here with the binoculars, right? Where the light ray comes in, and it actually is changed direction by the prism, and that's also what shifts it off center slightly. So if you've ever looked through binoculars, sometimes the main ends are not right in front of your eyes. And it's because of that redirection of the light that takes advantage of total internal reflection. Another really powerful application of total internal reflection is fiber optic cables. So fiber optic cables have a core material that has a much higher refractive index than the cladding, than what's around them. And so because of that, the light ray is sent in at an angle that will always be greater than the critical angle. So all of the light will stay within this, even as the cable bends. So you may have seen this if you had one of these lights as a kid, where it has little lights coming out of the end and it's pointed in all directions and it's free flowing, very cool. It's a fiber optic cable. It's also used in a lot of electronic applications because you can get a really good signal and not lose it to other sources. Here's an example in medicine of an endoscope, specifically looking at the lungs, so bronchoscope, I think, where there's a fiber optic cable that's able to bend all the way down into this person's lungs and see, even though it's bending, it's able to keep the light source within because of total internal reflection. And to see this in action, I have a video here, which hopefully it will play for us, and we'll be able to see it okay. It's looking at total internal reflection known as a laser waterfall. So with the laser waterfall, there's a stream of water that's coming out of a pool of water, and the laser is shining straight through the pool. And notice as the water drips lower and lower, the laser light stays within the water. It doesn't go outward at all. So the laser beam of light is redirected to stay within that water. Really cool to see. So total internal reflection, useful. And to get that, we need to be able to calculate that critical angle. This is a mini section that I'll fit in here, section 26.4, which is looking at polarization and the reflection and refraction of light. This has to do with another specific angle known as Brewster's angle or Brewster's law that says if you have light that shines at theta b, at Brewster's angle, and the incident angle, then when it's reflected off of the water at that same angle, it's going to be completely polarized, even if it was initially unpolarized. The refracted light will be partially polarized, but the reflected light will be completely polarized, which is interesting because in general, if you reflect light off of a surface, like off of a mirror, it is partially polarized. But there's this one particular angle, which you can find by taking the inverse tangent of N2, the secondary material, divided by N1, and you can know that the light will be purely polarized at that particular angle. So that's a bit of an aside, but it's worth pointing out, and you do want to keep this equation straight from your critical angle equation because they look very similar, but they're used in very specific instances. So that's a note you might want to add to your crib sheet. Okay, we will wrap up there.